Should we start?
Good afternoon, everyone. Welcome to the 12th webinar of ITA's Working Group 23 on design and construction of shafts. It's a pleasure to have you all with us, and we appreciate your interest and participation in this session. As the animator of Working Group 23, it's my honor to host today's webinar and introduce a topic that is fundamental to many underground projects, which is the design and the construction of shafts. This is a topic that many organizations, companies, and researchers have explored in order to consolidate the best practices around shaft construction. Among others, Working Group 28 of the French Tunneling and Underground Space Association has worked on this topic, which has led to the publication of two key recommendations. One is focusing on deep shafts, and the other one is focusing on shallow shafts. And these texts aim to provide comprehensive tools for a better understanding of the different types of shaft projects and the specific considerations that come with each method. Today's presentation will give us a detailed overview on the content of these recommendations, highlighting key insights and design criteria, construction methods, and real-world applications. And to walk us through this important work, I'm pleased to introduce our speaker, Mr. Clément Gaudry. Clément is a project manager at AFTES and with hands-on experience in shaft design and construction, and also in TBN tunneling. He was involved in several major projects such as the French Deep Geological Nuclear Waste Disposal Project, Line 18 of the Grand Paris Express, and the utility gallery for the Olympic village of Saint-Denis. Clément has been actively involved with Working Group 28 of the AFTES in the past 10 years, and he also recently joined the ITA Working Group 23. And we are delighted to have him with us today. Before we start, I would like to ask everyone to switch off your microphones, please. And if you have any questions, please type them into the chat box. The questions will be answered at the end of the presentation. And without any further ado, I hand it over to Clément for his presentation now. Clément, the floor is yours, please.
Thank you very much, Siamak, for the introduction. I'm very glad to be presenting these recommendations that have been published by AFTES Working Group 28 and give you a bit of an overview of what they contain. A couple words about me that has already been presented by Siamak. So I'm a project manager for AFTES in France with 10 years of experience, involved in some major projects, mostly in France, and also involved in the AFTES ITA and promoting the the underground work to the younger generation through AFTES young members. So I'm an event coordinator. A few words about AFTES. So it's the French Tunneling and Underground Space Association that was created in 1972, so more than 50 years ago, has more than 1,000 active members and currently 26 active working groups. These working groups have been publishing more than 100 recommendations in French, and 60 of them have been translated in English. So not doing so bad with the translation so far. AFTES is organized with 7 operational committees and 3 regional delegations. And the subjects that are being treated in the organization is like very diverse. You can see we have subjects like planning, socioeconomic, legal aspects, ground conditions and geotechnical conditions, TBMs, conventional tunneling, blasting and mucking out. We have grouting and waterproofing, and transversal tasks, even maintenance and rehabilitation. So all the aspects related to underground works are covered by the by AFTES and the working groups. So you will find here the list of the recommendations that have been published and the ones that are available in English as well. The slide is to summarize the main reference that are existing about shaft design and constructions, and that are the references we've been using mostly for the recommendations. So the first one is a handbook, tunnel engineering handbook, that has been published in 1996. We have the work of Working Group 23 from ITA that has been presented already by CIAMAC. So the definitions and classification recommendation published in 2021. Couple of recommendations to be published, I heard this year from CIAMAC, so about site investigation and thinking methods, if I'm correct. We are also using the Eurocode 7 and the application norms, which are the 94-262 about deep foundations and the 282 about retaining walls, and of course their application handbooks. So as CIAMAC presented, we have two recommendations that have been published, one on deep shafts and inclined galleries, published in 2008, only available in French, and one on shallow shafts that is quite recent, has been published in 2023, and has been translated in English. So what is what do we consider to be a shaft? Is a vertical or subvertical structure with the length greater than the width. So it means it has a slenderness ratio greater than 1. And the limit that we set between shallow and deep shafts is around 50 meters. So why this boundary at 50 meters? It's not really a strict limit, but it's based on the feedback and the experience of this kind of works. And we found out that there was under 50 meters depth, there was no requirement to guide the handle loads in the shaft. And also the safety standards would allow the personnel to be working on the excavation phase. And that being said, it allows for the use of conventional equipment that you would find in civil engineering works, and more traditional methods also used in retaining walls. Up, when you're over a depth of 50 meters, then what we would see is guiding the handle loads in the shaft and specific sinking equipments. So as an illustration, you can see on the top picture very simple equipments for a shallow shaft and a whole equipment with a steel framework structure, winches, cables, and everything for a deep shaft. In terms of functionalities, we can set some differences between deep and shallow shafts. Shallow shafts, because they are more accessible in terms of construction cost, planning duration. They don't require specific equipments. They allow for a wider range of projects. So this is, for example, the project I'm working on right now, the line 18 of Grand Paris Express. You can see for a 35-kilometer metro line, we have 22 service shafts. All of them are shallow shafts. Deep shafts, on the contrary, they're long-term, higher cost, and also higher risks project, which makes them less common. As an example, in France, in the last decade, I think we had about 2 or 3 projects total. So very unusual, I would say, projects. That brings us to the first recommendation about deep shafts and inclined galleries, published in 2008. So the text was published, as I said, in 2008, and it was the goal of this text was to preserve the knowledge on shaft sinking, because the context was, as I said, a scarcity of projects in France after the deep mines were closed, after the industrial era was ending. The text was mainly focused on the construction methods and the equipments associated, and it does not cover the shallow shafts, so less than 50 meters depth. You can see the, I think, last projects, main projects of deep shaft that have been achieved in France. So the CIGEO laboratory for the future nuclear waste disposal, passive penstock shaft for hydroelectric project, and the Avrieux ventilation shafts that are for the Lyon-Turin project. So the recommendation includes this very interesting scheme that would give a definition of what is a shaft, what is a gallery, and the limits between subvertical shafts, inclined shaft in terms of angle, and inclined gallery. What you would also see is the type of material and equipment that could be used depending on the slope of the gallery. So it's illustrating that up to 25% slope, we could use conventional equipment, and above that, specific equipment has to be used because it's not suitable, because the traditional ones are not suitable anymore and cannot function. So again, that's quite a general consideration, but quite interesting. The functions of deep shaft, so they're mostly related to the type of projects. We have, of course, the mining related functions, personal access, ventilation, and material extraction with the skips that you can see here. Here you have a scheme of usual, very typical scheme of a deep mine. Hydroelectric related functions, for example, here you have the Nandedance project, and here I think it was the Passy penstock. So the shafts, they have functions of decompression, decompression shaft, and or water inlet or outlet. Another type of projects that are, I think, becoming more and more important is the deep geological storage. Could be for example, nuclear waste, as the illustrations here. So the first one is the CIGEO project in France. These pictures are taken from a project in Germany where they are repurposing an existing mine into nuclear waste disposal project. This brings us to the design constraints of deep shafts. So the regulatory framework is, I think, one of the main aspects to take into account. In France, the Code of Mining is the main text for that. We also have the validation of the work safety agencies to be considered, so they can have handbooks on security management. And for the sinking equipment, we are also subjected to European standards. So the first one is about load handling, I think, equipments, and the second one is about machines. The geotechnical and hydrogeological context also plays a big role in the design of deep shafts. I would say mostly the groundwater condition. I'm probably going to say it a couple times in the presentation, but they're really the key to a successful shaft project. Local and environmental considerations are also important. The access to the work site, the available footprint for the works, whether you have a water disposal possibilities. The excavated materials management is also very important nowadays, and as well as the impact on the environment, talking about vibration, noise, and dust. The functions of the shaft in operation and also in temporary functions, they determine usually the cross section and or the diameter of the shaft, and also the lining required, so whether it's watertight or not. I will now describe the different methods that are given more into details in the recommendation. So first, we're starting with the downward sinking methods. So it means downward sinking that we're going from the surface to the bottom of the shaft, and we're achieving that whether with a blind shaft that we don't have a pilot hole, or with an access at the bottom that we see at the end of. I'll show you later the methods associated. So the traditional method is drill and blast. I think it's one of the mostly used method, and it requires a specific sinking equipment. I was showing you earlier the head frame, the hoist, and the winches system. We have a galloway that allows for people workers to access either the excavation phase or the walls of the shaft during excavation. We have drilling equipment and also mucking equipment. So these methods allows for quite various cross sections and diameters shaft. The depths that can be reached are up to 1,000 meters, even more in some cases, and very commonly used. So we have a lot of feedback on this method. And it allows also to manage dewatering and the water coming from the ground when the flow rate is not so high. So the disadvantages are the risk of flooding with permeable grounds and the presence of groundwater. So we have this rule of thumb saying that above 10 cubic meters per hour becomes very difficult to advance and keep going with the thinking of the shaft. The advancement rates, sorry, are quite low because you have to work step by step and quite slow compared to mechanized methods that we're going to see later. And also the design of the shaft sinking equipment is quite important for each project. And we have also some extra hazards in case of in terms of health and safety, I would say, because it requires a lot of personnel working in the shaft. Here are some illustrations of these methods. So you can see here the galloway used to as a working platform in the shaft. It's suspended through cables to the head frame structure. You have the mucking equipment, the jumbo that you see here, that are usually attached to the platform, and the hoist and the winches system here that are allowing the different equipments to be moved in the shaft. And so you can see it's a very complex equipment that the design has to be appropriate to each project. I was mentioning the control of groundwater and to manage the water inflow in the shaft during the construction. So the way to do that in a conventional method is to either from the surface level when the groundwater is on the surface to use injections or ground freezing, even jet grouting techniques to reduce the permeability of the ground. And when it's a deep aquifer, then you have to excavate a chamber to allow for pre-treatment before continuing the shaft sinking. The lining that are and the support that are usually associated with this technique. So in terms of support, it's quite similar to tunneling, conventional tunneling. So bolts, wire mesh, shotcrete, steel ribs. And the main goal is to avoid instability of the shaft wall for the workers and to protect the workers. And the lining, depending on the functions of the shaft and of course the geological conditions, can be cast in concrete, so not watertight, or steel casing in watertight projects. Precast segments are also something that's been used quite a lot in shaft sinking and lining. The second method is what we call the shaft drilling, so big hole in French. I'm not sure. I mean, in French literature, we use big hole for this technique. So it's basically a drilling equipment, but bigger size, as you can see. So the excavation is achieved in water or slurry uh, um, slurry bentonite, and it allows to for removal of the muck and that is being transported by the bentonite and then treated on with a treatment plant, same as slurry TBM. So this technique is interesting because it has a good advancement rates. Uh, the bentonite can stabilize the shaft walls and also control the groundwater inflow. The equipment is reusable for many projects, and you have no personnel at all in the shaft, so quite good for health and safety. The disadvantages of this technique is that the diameter in the initial drill is limited to 4 meter, around 4 meter. The depth, maximum depth, the feedback we have was around 400 meter. And this is mainly because the deeper you go and the bigger the diameter is, the more forces you have in the axle, and it requires very strong axles, as you can see in the picture here, and there's a limit for that. This method is also not very adequate for permeable grounds because you would have the bentonite going in the ground, and you would have a loss of bentonite in the excavation. And as any drilling operation, the verticality control is very important. The types of lining associated with this technique is usually a steel casing that would be installed in the bentonite and then grouted to the wall of the shaft before removing the slurry of the excavation. Another downward thinking method is a mechanized, shaft thinking that has been developed by Ereknecht quite recently, actually. It's it's quite interesting because it can have faster advancement rates, and it's also safer for the workers because no one is at the front. Here is like a specific a phase that the machine is not working, but usually the excavation arm is working independently, doesn't need anyone at the front. And it's also more adaptable to different geological conditions. This is not covered by the recommendation because it's quite a recent development, so it was not didn't exist at the time of publication of the recommendation. So the second type of methods are the pilot holes thinking methods. So it's basically raise boring that I think is quite common and widely used, and the shaft enlargement methods, either mechanical or with drill and blast, also exists. Um, these methods are interesting in terms of advancement rates. The equipment is also quite reusable from project to another, and there's because it's mechanized, you have very limited personnel, no personnel at the excavation phase. And the equipment for raise boring is quite limited and can be installed in very small, very reduced footprint areas. The disadvantages are the diameter that is limited up to 5 meter in the initial drill. The depth for raise boring is also limited because of the deviation, the possible deviation of the pilot hole. You don't have any groundwater control. That's a big problem for this kind of method. So in aquifers and permeable ground, it's not so suitable. And there's also for raise boring no possibility to install support during the excavation. Incline galleries, so it's mostly techniques derived from shafts or other methods. You have here some illustration of TBM for an incline gallery. You have here a machine that is a auger boring machine. Here something that some methods that looks quite similar to drill and blast method with some kind of platform, working platform down the gallery, and here a head frame to kind of suspend it. And another method I think that wouldn't be used anymore nowadays is like the what we call in France the Alimac methods from the I think company building these machines, which is basically an elevator on a rail that travels usually upwards to sink the gallery from downwards from the bottom. The recommendation is also including some considerations for dimensioning. They're more like general considerations about the loads that has to be considered for the dimensioning of both the support and the lining. Some aspects of the monitoring are also discussed in this recommendation, but it's not a very developed part, I would say, of the text. The text also includes some appendices. So the first one is a table with some shaft thinking reference with different techniques. quite complete, and I think mostly European reference, but they go back to 1950s or something like that. So quite a big work that has been achieved with these tables. And also comparison of the different thinking methods regarding different criteria. So the conditions that are adequate for each method, the main characteristics of associated with each methods in terms of diameter, depth, uh, ground resistance that is allowed, the quality of the works, verticality, the excavated walls and they're regular or not, and the damage of the rock mass that can be caused. Types of lining associated as well, mentioned that earlier, and the technical risks for each method and the main corrective measures that can be set. And the last criteria is the impact on the environment. So quite a complete table, very, I think, useful for the selection of the thinking method. Okay, so that sums it up for the first recommendation. I will now go through the second one on shallow shafts. So I didn't participate in the first recommendation, but this one I've been part of it. So it's I would know a little bit more about the history of the text. So there was a first version that was published. That was I mean not published, but initiated right after the deep shaft recommendation, and it was submitted for review to the technical committee of AFTES, but was not accepted. So the main reasons for that are that the focus was mostly on the construction methods, as the first recommendation was. It was not really developing the dimensioning aspects, and it was a bit too general and didn't highlight the specificities of shallow shafts. So that resulted in the standby of the working group 28 for 8 years, quite a long time. And eventually, because the recent projects, they brought some feedback, some new construction methods were used, and the application range, as I was presenting before, is more important than deep shafts. Then it was decided to restart the working group 28 in 2019 with 13 new members and 2 previous members. And the same animator was Pascal Guédon. So here are the 15 members of the working group. What's interesting is to highlight that there were 3 young members under 35 years old. Very diverse team from design companies, construction companies, a person from a control agency, and a shaft construction expert with more than 40 years experience. So we started the work in 2019, September 2019, so right before COVID-19 lockdown, and we held 15 meetings for 2 years, and that brought us to send the first consolidated version in December 2021, so 2 years after the start of the working group, and the finalized version after review was published in May 2023. So I will go into the different chapter of this recommendation and give you a bit of an overview of what they contain. So the scope, as I said, is about shallow shafts, so under 50 meters. And from the beginning, we wanted to set that the excavated diameter should be generally greater than 3 meters. That is not something that is an obligation, but we thought that for safety reasons, it's it's wiser to go for bigger diameters. The largest dimension here in horizontal plane is less than 50 meters. That's the rule of the slenderness ratio. That should be greater than 1. And we didn't want to include the public access structures because they have specific crowd management considerations that are not covered in the recommendation. And it's important to note that this text can be applied to the upper part of deep shafts, the 4 shafts that are used to introduce the shaft sinking equipments. So here is a picture of a project that is actually not a shallow shaft. It's the IGR station in the Grand Paris Express project. It's a 63-meter diameter and 55-meter depth, so slenderness ratio is less than 1. But eventually, the concepts that are developed in the recommendations, they can still be applied to this kind of structures. In terms of functions, as I said before, the shallow shafts, they have a wider range of use, either temporary or operational functions. So you can see here, for example, TBM launching shaft. Here is a typical access emergency exit and ventilation shaft that is apparently also used as a TBM dismantling shaft. So these, because the shallow shafts have a wide range of functions, they also require to adapt to different site constraints. You can see on the first picture, for example, a shaft that's been achieved right under I think 20 plus story building. So because of these environments and the very different environments that we can have for these kind of projects, the data collection is very important, and we defined the what we call the shaft model. As you can see here, is a scheme that includes all the main information that would be required for a shaft project. So of course, geological, hydrological context, the geotechnical surveys as also to be mentioned, the existing structures. You can see here a building, here I think underground network, here another metro project that or existing metro, sorry. And it can also include the uncertainties for risk management, whether the thickness of a soil layer or the level of the water, groundwater. And another aspect that's important nowadays is the characterization of excavated materials. And this allows to define the construction methods and the structural design of the shaft. And in the recommendation, we define the minimal requirements for investigation that has to be carried for a shaft project. This slide is a bit of definition of the terms. I think these terms you would probably know them if you're in the tunneling industry, but we wanted to give a proper definition. So the support is what you would install during the excavation, and that would stabilize the walls. The pre-support is installed before excavation, so that would be, for example, piles or a slurry wall, these kind of things. And the pre-treatment that would be installed, that would be, sorry, methods that would improve the characteristics of the ground, either mechanical characteristics or permeability. So the way we divided the different construction techniques is either they present support, pre-support, or pre-treatment. and we put them in each categories. So we have, I'm not going to go into detail for each of the methods, because you have all these informations in the recommendation, but we have the traditional shafts that only have supports as the excavation is carried, composite wall with a partial pre-support, could be piles, could be steel beams. We have contiguous piles, second piles, sheet pile wall, of course, the diaphragm walls, jet grouting and soil mixing as well, that are in between pre-support and pre-treatment. And also techniques as ground freezing that are carried on for shafts in water conditions. We also have a technique called caisson shafts, where you would sink the lining as the excavation advances. Could be the traditional one, and I think you might be more familiar with the mechanized version of it, developed by Eric Knecht again, the vertical shaft machine. That is a caisson shaft with a mechanized excavation arm and hydraulic mucking. So we summarized all these different methods in a table, giving a lot of information about either the pre-support or the support included in the metal type in the method, sorry, the structural lining associated, the geometry that we can have, the classic applications, what are the limitations of each methods, and what are the equipments that are usually used uh, for the works, the footprint that is required for to achieve these methods, the nuisance associated, and the construction speed, and lastly the applicable standards in the, I would say, European and French standards. So might not be applicable for anywhere in the globe, but still interesting. So all the methods that I presented before are covered in this table. So it's a really a great tool for to help decide which methods to use for construction of a shaft. We also have some considerations for the current and future developments, mostly considering the mechanization of shaft sinking. Some also aspects about the cross section of shallow shafts, because the structural constraints are not as much as the deep shafts. It allows for an optimization of the section and various shapes. So as you can see here, rectangular cross section. Here something that looks like I would say a keyhole or something like that. Um, elliptical shaft, bilob, so very different types of cross sections. Another important aspect is the openings that are being carried usually at the bottom of the shaft. So most of the projects, they require openings to connect the shaft to another underground structure, usually I would say a tunnel. And so these specific areas, they require like some consideration about water table control, the structural reinforcement. As you can see here, they cast in a thick layer of concrete to manage the probably deformation and the structural resistance of the wall. Waterproofing also in these areas is quite a challenge, and also the surface settlements that can occur. The recommendation has a quite developed chapter on dimensioning, so I would not go through everything because it's quite dense, but it covers very different aspects. and the very practical aspects of the dimensioning of the shaft. It's not really a general methodology, I would say, to dimensioning, but it gives a good understanding of the assumptions and what is required to consider for dimension of a shaft, shallow shaft project. And it's also describing the usual dimensioning methods that are used. Um, Associated with this chapter, we have appendices on dimensioning methods that they go a little bit more in details on specific aspects. So it's 5 appendices. The first one is about the specific case of circular shaft and gives kind of a dimensioning guide, including openings at in the wall. We have appendix on how to evaluate the pressure on traditional excavations, something about fiberglass reinforced structures, seismic checks, and soil deformation assessments. The recommendation also deals with safety and emergency management. So for this topic, what's important to remember is that local regulations, they can vary from a country to another, but it's, I would say, every shaft project needs risk analysis to be carried on, and that allows to evaluate the main risks that your project would face. So the most common ones is the connectivity with between staff and load handling in the shaft, the fact that we're working at heights, the reduced mobility for evacuation, and also aspects like air quality, noise, and vibrations that can be also harmful for workers. And it also gives some ways to mitigate these risks. The instrumentation, monitoring, and traceability is also described in this recommendation. So in terms of geotechnical monitoring, how the ground is behaving in response to the construction, the strain and stress measurements in the support and definitive structures, and also the environmental monitoring. We, during this, the work of we did on this recommendation, we decided to initiate some what we called shaft project data sheets. So it's basically one document per project. So we have around 30 projects that have been listed, and we're publishing these data sheets in the quarterly magazine of AFTES. It's called Tunnels and Underground Space, and they're also like available for free access on the AFTES website. And they're, as you'll see, they're translated in English. So don't hesitate to go and check them. They're available for everyone. As you can see, they have a lot of information about the projects, the type of shafts with images, cross sections. What are the geological conditions of the project, and also the feedback on the works. So duration of the project and advancement rates, these kind of topics. So it's quite a complete database of projects. So I would really recommend to check them. I would finish this presentation with the perspective of Working Group 28. So as I was presenting the data sheets, it's like a endless endless source of work if we want, because because we want to enrich this database with new projects and including the specific context, the innovative methodologies being used, and so that's a work that we can carry on for many years. Also, a new version of the recommendation on deep shafts could be considered to include the recent developments. I was mentioning the shaft boring rod header from Agnecht, the feedback of the recent projects in France and also worldwide. Dimensioning methods could be developed in the new version, and also the latest update on regulatory framework that will probably appear really soon. And of course, an English translation would be quite interesting as well. And I would finish by saying that it would be also interesting to increase the collaboration with Working Group 23 of ITES, ITA. So I think that's the reason why also I'm involved in Working Group 23. So hopefully this will happen very soon. I would like to take the couple minutes that I have left to thank Pascal Guédon, who has been animator of Working Group 28, and Bernard Lannes, who's the expert in shaft construction. So I want to thank them because they've been sharing knowledge to a lot of people, whether through the recommendation or also giving lectures, and that's very it's very um, it's very amazing to have these people sharing everything they know. They share their success, but also the projects that failed. They don't hide anything. So it's for the profession. I think it's really important to have people like Pascal and Bernard. So thank you to you both. And I think I saw Pascal in the attendance. So thank you, Pascal. That's it for the presentation. I will now see if there's any question in the chat.
Yes, Clement, thank you very much for your very interesting presentation.
Thank you, Simon.
We in that's our 12th webinar today. In our past webinars, it was always been interesting to see how different countries have different approaches to the design and construction of shafts. And in this case, how similar your work has been to the ideas we had. We have completed recently a document in ITA's working group number 23 for the selection of construction methods for shafts. And we also have reviewed different construction methods and provided some sort of decision-making charts and decision-making trees, which should help in selecting the different methods. But it's interesting to see how the approaches are similar or different. And we certainly look forward to more collaborations with you and your teams in any case. So if anybody has any questions, please type them into the chat box and I will read them out to Clement and he will provide you with the answers, please. I have a quick question. Your recommendations, I have noticed you have provided several tables. Are they, in addition to comparing the different methods, also being used in selecting the different construction methods or not?
We didn't want to go as far as giving like I would say like algorithm that would select the selection, because like with thought that it's good to keep in mind that there's a lot of parameters in the selection, and it's I think good to keep the engineers to give them tools to decide, but not decide for them. So that's why we kept it in a way that it's a tool, but it wouldn't be it wouldn't give you the answer at the end.
That's always wise, but every project is different. You're right.
Exactly.
Every project has different conditions. Every project has a different geology, different geotechnical conditions, different
Yes.
water table conditions, different groundwater conditions. And
even if you think about the methods, some countries, they're more familiar with specific ones, so they would
exactly,
encourage, for example, raise boring or whatever.
exactly.
But that's also
Yes,
very cultural input that we cannot put in this table.
sure, definitely. It has been very interesting. Thank you very much.
Thank you
And
for the opportunity to present, and it was a
thank you.
nice time presenting, for sure.
Definitely. And we look forward to see you in our meeting in WTC and everyone else as well. Thank you for participating, and we look forward to see you in our next webinars as well. Thank you very much, and see you later. Bye.